Hi everyone, this is Miss Helms, and this video is to help you complete the notes for your special right triangles, in particular your 45, 45, 90 special right triangles. So, you do not have to watch this, but if you need help filling in these notes, please go ahead and follow along. So, all of these special right triangles are right triangles. So because of that, we can use the Pythagorean theorem, which we learned before. So the Pythagorean theorem is a squared plus b squared equals c squared. So we're going to use that to generalize a pattern for these special right triangles, in particular, again, the isosceles right triangles or the 45, 45, 90 degree angle triangles. So starting with the first example, we're given that AC is 1 unit. So we're going to mark that in the diagram. Well, since this is an isosceles right triangle, we know that AC is congruent to BC. So therefore, BC also has a side length of 1. So to solve for AB, we set up the Pythagorean theorem. We know that 1 squared plus 1 squared equals side length of AB, quantity squared. 1 squared is just 1, so 1 plus 1 equals AB squared. So 2 equals AB squared. And to get AB by itself, we're going to take the square root of both sides. So AB is equal to the square root of 2. Next, looking at example number 2, we're given that now, instead of 1, AC is actually 2 units. So AC and BC are congruent since it's an isosceles right triangle. Therefore, BC is also 2 units. And then to find the side length of AB, we can go ahead and set up the Pythagorean theorem. So 2 squared plus 2 squared equals AB squared. And 2 squared we know is 4, so 4 plus 4 equals AB squared. 4 and 4 is 8, so 8 equals AB squared. And to get AB by itself, we're going to take the square root of both sides. Well, to take the square root of 8, we want to keep it in simplified form. So to take the square root of 8, we say, well, what are the factors of 8? Or how can we break up 8? So the square root of 8 breaks up into 4 times 2. And we know that we can take the square root of 4 and get since square root of 4 is a perfect square, since 4 is a perfect square, we know the square root of 4 is 2, and what's left under the radical? Well, we're left with that 2. So the square root of 8 really simplifies to 2 radical 2, so the length of AB is 2 radical 2. So at this point, you should start seeing a pattern. Taking a look, in the first example, we had side lengths of 1, and the hypotenuse was 1 radical 2. In the second example, we had side lengths of 2, and the hypotenuse was 2 radical 2. So to generalize this, we can come up with a general pattern in this last example. So we're told that AC is x, which means that BC is also x, since it's an isosceles triangle and the legs are congruent. So, setting up the Pythagorean theorem, we have x squared plus x squared equals AB squared. And that means we have 2x squared equals AB squared. To get AB by itself, we're going to take the square root of both sides. And to simplify this radical, well, the square root of 2 is, since 2 is not a perfect square, it's going to give us a decimal, so we're going to leave 2 under the radical. However, we can take the square root of x squared, and we'll just be left with x. So x, again, left under the radical is 2. So x radical 2 times radical 2 is the length of AB. And this is our general pattern. Again, as we said before, in example 1, our side lengths were each 1, so that meant our hypotenuse was 1 radical 2. In example number 2, our side lengths were 2, and our hypotenuse was 2 radical 2. So let's say I gave you the value for one of your side lengths, or one of your legs to be 4. Well, we automatically know the other side length is also 4, since the sides are congruent, and to find the hypotenuse, we could use this shortcut. So rather than going through the Pythagorean theorem, since it's a 45, 45, 90 triangle, and again, this pattern is only for 45, 45, 90 triangles, we automatically know the hypotenuse is 4 radical 2 based on this pattern. However, do not feel like you have to memorize this pattern. You can use the Pythagorean theorem just as we did in these examples to solve for the remaining side length. So it's a nice trick, it's a shortcut, but again, nothing that you need to memorize.